let's let z be a standard normal. That is, it's a normal random variable with mean 0 and variance 1. Okay, let's find the distribution of z squared. How does z squared behave? Okay, first, before we even do anything for real, let's just take a look and see if we can guess about it. Okay, so here's our standard normal. It's a standard normal density function, something like that. What happens if I square this random variable? What's the density function going to look like now? Well, you don't square the density function. Okay, remember, this function describes the behavior of the standard normal. So sometimes it's over here, sometimes it's over there, right? Usually it's right in around here. Every once in a while it's way off to the left or way off to the right. But if this variable takes on the value over here, then by squaring it, it's going to then become positive and squared, right? So it's probably going to look something like this or like that, right? Is what the density will look like. Something like that. Sort of right skewed is what they call it, and certainly going to be non-negative. All right, so let's see. How does this thing behave? That is, we want to find the distribution of z squared. Okay. All right. We'll do this with the method of moment-generating functions, right? Okay, so I'll just find the moment-generating function for z squared, and if it turns out to be something familiar, then fantastic. Okay, so this is, of course, by definition, the expected value of e to the t z squared. I know how to carry that out. It's just e to the t variable squared, right? Like that. This is a little z. This is a big Z. Times the density for a standard normal, right? It looks like that, over root 2 pi dz, right? Now, I can bring this stuff together in the exponent there. This is just going to be the integral over the reals, 1 over root 2 pi e to the tz squared minus z squared over 2 dz. In fact, I can bring that together a little bit more, make it look a little nicer maybe, because, well, let's see, what is this looking like? I guess negative z squared over 2, can I say, times 1 minus 2t, I think. We could write it like that. Okay. Now, take a good look at this. This is the mark of a good mathematician, folks. Physicists tend to be pretty good at this stuff. Some of them, anyway. Take a look at this. Does this look familiar at all? Yeah. Integral over all the reals, 1 over root 2 pi, e to the negative variable squared over 2, and then something else over here, but whatever. It looks a lot like, the integrand looks a lot like the normal density. And in fact, you know what? Here's what I'm going to do. I'm going to play. So I'm going to actually adjust it so that it is a normal density. And then I can carry out this integral real quick because I know I'm going over all the reals. If all this was a normal density, then this integral would just evaluate to 1. So that's what I'm going to do. First of all, let me rewrite this a little bit so that you see what I'm going to do here. E to the negative z squared over 2 times 1 minus 2t to the negative 1, okay? I'm going to put that down there in the denominator of the exponent. And then, so here's what I'm going to do. In the normal density, all that stuff right there, this is equal to the variance, right? So I'm going to set that equal to the variance. But now then I need also to put a sigma over here, standard deviation, and also here. So I'm multiplying and dividing by sigma. Perfectly legal move, right? I'm just saying, you know, let this stuff be sigma squared. Now, all this stuff, all this integrand evaluates to, where's my red pen? There we go. This integrand will evaluate to 1, okay? Pretty slick, huh? And I'm just left with the sigma out here. Did I say integrand evaluates to 1? The integral evaluates to 1. Sigma here then is just going to be the square root of 1 minus 2t to the negative 1, or 1 minus 2t to the negative 1/2. Okay? Now, if you look that up, you'll see that that is, in fact, the well-known moment-generating function. It's the moment-generating function for a chi-square random variable. Okay? It's a moment-generating function. Let's see. I'm looking it up right now. And you can find this on the interweb or in your book. It's a moment-generating function for a chi-square random variable with 1 degree of freedom. How about that? Fantastic. Here's an important theorem for some statistical applications for sure. Let's let x1, x2, xn, so let these n things be independent random variables, normal random variables. These are all independent normals with means like this. They can have different means. Okay, the mean for the ith one is mu I, and the variance for the ith one is sigma I squared. So just like we had previously. They're independent normals, but they have different means and variances. So again, you might think of a picture of that kind of thing like this. Like, here's the behavior of one of them. Maybe another one sort of tends to be further to the right, but more spread out. And then maybe another one still, is more spiky in behavior, something like that. So we already know that if you take one of these guys and square it, it behaves like a chi-square random variable, right? Okay. Well, what happens if you square them all and sum up the squared variables? Turns out this also behaves like a chi-square, but it has n degrees of freedom. N degrees of freedom. What's a degree of freedom? I don't know, and I don't care. It doesn't really matter. It's just a parameter for the distribution. You can think of it like that for now. Okay, so here's the proof, and of course we're going to use moment-generating functions for this. So this goes like this. The moment-generating function for the sum, I goes from 1 to n, of these z sub I squared of t is the expected value of e to the t times the sum z sub I squared. I goes from 1 to n. Okay, so then that equals expected value of, this is, I can write this as a product, right, of e to the t z sub I squared. I goes from 1 to n. Okay, and this is by 7th grade math, right? If you were in the 7th grade, you learned that in the 7th grade math class, or some previous math course. Maybe you took it last year, I don't know. Okay, and then also we know that the expected value of a product of independent things is the product of the expectations. This is by independence. Okay, here's our symbol for independence, I guess. Okay. And so that's the product of the expected values, e to the t z I squared. Right? All right, goes from 1 to n. Now, I already know what this is from our previous example, right? This is the moment-generating function for a chi-square random variable, right? So, and this is 1 minus 2t to the negative 1/2, right? Okay, so all of this stuff is just it's the product of this with itself n times. So it's just this stuff raised to the nth, or just 1 minus 2t to the n over 2. And if you look this up, this is the moment-generating function for a chi-square random variable with n degrees of freedom.